So, hi everybody, and first of all, thank you very much for having me here. And you have some brochures on our project, now the commercial part. So take one home. So basically, I'm a professor at the University of Girona, and I'm the coordinator of this project in which Melanoma Patient Network Europe is involved, which is the iToBoS project, as you have here, Intelligent Total Body Scanner for Early Detection of Melanoma. And if I tell you about the project basically is in this call of digital diagnostics. I tried this before, and it was working, so I'll give it another shot. Okay, no, thank you. Okay, the call is digital diagnostics, and this means that the aim of the call is to develop tools for supporting clinical decisions. And this was a very competitive call, but before I tell you about the project, I want to give you a personal note on my background. So basically, I have many dysplastic nevus, and for many years, I've been doing this total body mapping follow-up. And as I was going through this process, I found that this was a very tedious operation. At the time, we were doing MoldMax and, taking pictures of every suspicious lesion, that when you have a lot of lesions, this takes a long time. And then I also felt that this was an error-prone operation that depends a lot on the dermatologist or the technician that it's taking the pictures and deciding which ones you want to check and to follow over time. So we had Des Tobin before, that he took us on this wonderful journey from the hair follicle to the melanoma. And what I want to, now that I'm talking about me, I want to tell you to a journey that is even deeper. In this case, we're going to the ocean. My background, the lab that I coordinate at the University of Girona in Spain is a lab in which we work in underwater robotics. And what we do is we build underwater robots. These are different robots, all of them made in Girona, in Europe. And these are autonomous robots. We send them to the water, and we want them to freely explore in an intelligent way and hopefully not get lost. Okay, and the things that we're doing is basically going to these type of places. Like this is an example of an hydrothermal chimney in the Mid-Atlantic Ridge. This is more than 1,000 meters deep, and the robots have cameras and take images. And what my research, my lab research is known for internationally, is because we build maps of this. This is a 30 times real speed of this hydrothermal chimney. But from this, we build these beautiful maps of a given area, the area that the robot has explored. It can be bigger, smaller, it can be 1 square kilometer. And then we build this map to assist geologists and biologists in monitoring what is going on there. And 2 years later, we go to the same place, we put the robots in the water, and they do a different trajectory, but they cover basically the same area, and then we can go back and build a second map. This is a very high-resolution map in which you can see the mussel colonies that are there. And the things that we do is just take the two maps together and compare them and say, what has changed in 2 years? So this bacterial mat here is getting bigger, this colony of mussels is getting smaller, and we understand things based on that. And of course, this takes us back to the Earth, which is when I started getting all these lesions mapped, I was talking to my dermatologist and saying, look, why don't we try to do something about this so that we automate this process? And we built this cabin. That was the first prototype that we had, in which we have several cameras, we have polarized light, and we started taking very high-resolution images of the skin. We have this rotating platform where the patient would stand, and then we will take several images of the skin of the patient, and in this way we will get this 3D map in which then we can locate every individual pigmented skin lesion and use this as the baseline for having a second map 6 months later, scanning again the same patient, and then locating the same, registering, aligning, because the patient breathes, moves, and it's exactly the same problem that what we were doing underwater. But in this case, we could automate it and have it in a more, I would say, less tedious and more scheduled way. And this led us to the iToBoS project. In the iToBoS project, the main objective is, again, to develop tools for early detection of melanoma. And the way in which we're doing this is basically taking these full body maps, but we also wanted to use other sources of information. I don't want to just compare one lesion to one lesion. We wanted to understand the patient, to see what are all the lesions that this patient has, what are they like. And we can map them, but then we can combine this with all the information that we might have about the patient. And this will be the genomics through a saliva sample, and medical records and demographic information. And we want to put, what we are developing in iToBoS is taking all this together and developing the machine learning, deep learning tools to develop what I call this AI, artificial intelligence, cognitive assistant. And this is basically providing us with what is the risk of every individual lesion of a given patient, taking and personalizing all the data that we have about this patient. And of course, when we do this, we want to do it taking into account that then we want to provide feedback to the dermatologist. And this is why we have this branch in the bottom that says intelligent human-computer interface. So we don't want the cognitive assistant to be a black box, like most AI systems that just produce a prediction, and you don't know why they're doing that. They are saying, this is not, or this is a melanoma. We want the system to be able to explain itself, to provide insights about why a given lesion has a given diagnostics. And this is what we're working on, and basically, it's not the only thing the project is about. We also wanted to improve the quality of the images that we are collecting from the patients. And this is why in the proposal, this was my draft of how I imagined. You see, it's very related to the previous cabin that I show you, in which I have several cameras, and these cameras rotate around the patient, and the patient has all these images collected in high resolution. When we started working in the project, it was right on the period of the where we were getting out of the COVID pandemic. And we were not aware of what was happening in the market, but we realized very early, which was that we had this microchip crisis that meant that it was very hard to get samples of cameras. The chip of the camera ran out of production. It was very hard to get encoders. It was very hard to get many, many electronic components. And in the project, we have Bosch, which is the partner that is building a new prototype of a scanner. In this case, it's not a vertical prototype. As we imagined when we started working on this, we decided, okay, we're going to do something more similar to an MRI machine where the patient lays, and then we have all these arches, and every arch has several cameras, and we're going to take images. And then the bed is going to move, and we're going to scan the patient with very high resolution, getting these very nice images. But the first prototype was supposed to happen on month 18, 1.5 years on the way of the project. The project is 4 years, so in the first 1.5 years, we expected to have already a prototype of a scanner. What happened was that because of the lack of components in the market, we saw that this was getting delayed. So we had to take some decision. And then we put in place a contingency plan. And what was the contingency plan? We just looked at the hospitals that we had in our consortium. We have 3 hospitals, the clinic hospital in Barcelona, the melanoma unit, then the hospital in Trieste, and another hospital in Australia, in Brisbane. And then 2 of these hospitals had this other machine, which is what we found it was the most similar machine to what we have envisioned initially. This is the Canfield Vectra 360. Basically, this is a machine that allows us to take this type of imagery. You see, it's quite similar to the type of images I was showing before that we were acquiring with our first prototype of a scanner. And we decided to use data from these machines to start developing the software, this AI cognitive assistant, so that we can advance. And in parallel, we continue developing our scanner. We do as much as we can, even if the market is delaying us in this radical way. But this was the way to cope with this market situation. And then, what is the cognitive assistant doing? the cognitive assistant is basically, as you see here, I start with this central part. It's measuring the imaging phenotype of the patient and trying to get this imaging risk score that comes from the images. So we have the full body images. In this case, with the Vectra, we also have dermoscopy of some of the high-risk lesions that the dermatologists detect in a given patient or decide that these are lesions that we want to follow. So we use all this information, the full body images and the specific dermoscopic images that they acquire. But we also measure the imaging phenotype of the patient. So we measure UV damage that the patient might have, what is the phenotype of the nevus that the patient has, that the patient has. And then if we have previous explorations, we also want to take into account the same thing that we were doing with our first scanner. Taking into account, is there some lesion that has changed? Is there a new lesion appearing in a place where we didn't have a lesion before? And we want to integrate this information for this imaging risk score. Then we also take this genetic risk score, which is the saliva sample that provides then with a measure in which we take into account the familial genes and the polygenic risk score. Because we don't have enough patients, we're not doing research on this, we just get an index, which is for us, the genetic risk score is a number between 0 and 1, and this is what we integrate in the cognitive assistant. And on the other hand, we have these medical records that I mentioned before, which are all clinical data and demographic data, age, sex, the traits of the patient, what is the hair type, the eyes color, the skin type, medical history, family history, and so on. And in this way, when the cognitive assistant says, this is my prediction for this lesion, it's taking into account all the lesions of that patient, all the information that we have about the medical records and the genomics that we have also measured for this patient. And it's a way to personalize this diagnostic or this assistance for the dermatologist then to take a decision. And of course, we do this, as I said, with this explainable AI. We have a team and a work package that it's only dealing with how to explain the decisions that this artificial intelligence model is providing to help understand all the decisions that we make. And then with this, we get this type of scans. At the moment, we are at the end of the second year of the project. We are collecting data from patients. We are anonymizing them, so we remove personal data. And what the doctors see is this 3D model. What the scientists see within the project are just small tiles that we cut from these 3D models, and then we can make predictions of every individual lesion. Of course, in the project, we're still working on developing the total body scanner. And this means that, for instance, for the imaging part, we have already some results. It's hard to see here on the screen because of the resolution, but the idea, what you should see here is that we have a better, higher resolution image on the right than we have on the left. And basically, the way we do this is by using a technology that it's called liquid lens. And we are developing, one of the partners in the project is a manufacturer of lens. And we want the cameras to look at the skin at a very high resolution. If you have ever taken pictures with a long focal length camera, what happens is that the depth of field, the part that is in focus when you use a very big zoom, is very narrow. Because it's very narrow, what we are doing here is we're taking this lens and we are shooting many different images. In 1 second, we can shoot 90 images. So the patient feels like there's only one flash, but in reality, we took 90 images at at slightly different depths. And then we combine all these images together through a technique that is called focus stacking. And in this focus stacking, basically, we are taking for every individual image, we check what is the part that is sharper in that image, and we generate this image on the right that is a combination of all the best parts, the well-focused parts of every image in the stack. And these are the images that then we feed to the cognitive assistant for doing diagnosis. And of course, after that, we could do something else that is called super resolution, which basically it's trying to improve the quality of the images. So basically, in a nutshell, this is the idea, and this is my personal story on how the project started and what we're trying to do. And I let me finish by saying that this is an effort in which we have 19 partners. Melanoma Patient Network Europe is one of the partners, but we have the 3 hospitals here. We have several research centers. In fact, Leonard is going to talk next from the Leibniz Universität Hanover. We have also some industrial companies. This is a live project and things happen in the project. Something else that happened is that Barco, for instance, sold his dermatology business to another company. So recently, now we are just negotiating with Barco so that they leave because they are very focused on this new company and they cannot participate in the project. But we are getting in a new partner, which will help us, hopefully, to get all the developments that we are carrying out, that they get to the hospitals and to the clinical practice once the project is over, or at least we want to have this pathway to the market so that this doesn't end up just with some papers, so that this ends up, in something that is tangible and that it's improving the life of the patients. So that's it from my side. Thank you very much. And if you have any questions, comments, curiosities, yeah, I see a question there.
My name is Lex van der Rijn. I worked for IBM Global Services, so IBM rings a bell. I discussed about 8 years ago with Microsoft an idea that based on genetics, you could also make a prediction about the future. For instance, PIK3CA gene mutation could cause overgrowth, or in cancer is also a common gene. However, the problem was, how do we get genetic data? GDPR doesn't make life easy. Is there anything you also have in mind for, unless maybe a next version, to take care or to take into account genetic data to have a future look and make some predictions about possible complications?
Just, it's a very interesting point, indeed. And in fact, myself, I'm an expert in images. And this is the first project in which I got exposed to this genetic information. And I saw that one of the nice things about these machine learning systems that can collect data from different sources is that they can integrate raw data in a very effective way. But one of the things we are fighting now is that we are, at the end, for this initial project, we are just going to have data from around 900 patients. 900 patients for this genetic information are 900 dots at the end of information. And because of anonymization and ethical issues and so on, we decided that we are going to get only just the index. But the way I see this is that in the future, this should be scaled so that we can increase the number of patients. And in fact, I'm working in this direction, in trying to get more hospitals and more patients involved in the future. And then we can anonymize this in a way that we can take the raw data with the safety that requires to preserve security and anonymization and so on. But probably we can exploit a lot more than what we're doing nowadays. So, but as I said, I'm not an expert in, in the field, but I think there's a lot of room for improvement there.
Hi, Rafael. You spoke about a clinical trial that you are preparing at University of Barcelona once you'll have the prototype in place. So can you tell us more about who you'll enroll, probably high-risk patients, from where, and so on?
Yeah, it's basically going to be, when the prototype is ready, we're going to place the 2 prototypes in Barcelona, at the clinic hospital, and in Trieste with Iris. And they're going to select, in this case, we're going to have a comparison of the quality of the data that we are getting with the Vectra, with the new imaging system, with the new model, and dermoscope information of selected lesions. And this is going to include 150 patients for this study. But unfortunately, because the European Commission doesn't like that you extend the projects beyond the bounds that they have. So, and because of this delay in the market, we're going to have much less time to collect data than what we initially foresaw in the project. But well, we'll do our best to collect as much data as we can, and and then try to evolve the technology as fast as we can. And I should say, and probably this is not the last project we're going to see in this line. My intention is just to, push this further away so that we make this a product at some point that could be used in the hospitals.
That's why I was thinking if you have a project afterwards, just focusing on implementation, how you bring something like this on the market and you scale in Europe. Because in the Eastern European area, for example, we use Photo Finder, and I think in most of Europe. And okay, what is your opinion about if you compare what you are going to build with that? People are asking us, and what is the difference between what you are going to build in this project and what is already on the market?
Yeah, the idea is that we believe that better quality of images will lead to better predictions. And then
integration of everything, genetic
and then if
clinical.
we integrate, because we could do the integration with the current scanners that are there in the market now. And this is, in fact, what we are developing right now at iToBoS, because we don't have the new scanner. But as soon as the new scanner is available, this software can integrate this information and provide better predictions if we get enough data. There are many if here. But so we need to train the models with the corpus of data that would allow us to improve. But this is the line of research that I think we have to push to be able to improve the results in the future.
Brilliant. Thanks so much, Rafa. Rafa's here. If you want to know anything about the AI, the machine learning that's behind this, please, he's here for the duration, so please ask him questions.
Yeah.
Thanks so much, Rafa. Really
you.
good.